Okay. So good morning, everyone. So last week, we started one chapter that is Haloalkane and Haloarenes. तो उसका हमने यहाँ तक कंप्लीट किए थे एक वन शॉट लेक्चर के साथ. तो आज हम ये चैप्टर को कंप्लीट करके इसके पीवाईक्यू सॉल्व करेंगे हम लोग. ओके.
Ma'am,
यस.
ma'am, can you speak English because I can't understand Hindi?
अच्छा अच्छा फाइन. ओके. So last week we started with this chapter that is haloalkanes and haloarenes. So we completed this chapter till this part, till SN1 and SN2 reaction. So today we are going to see the further part of this chapter. So I think today we'll complete this chapter, and after completing this, we'll solve the PYQs, previous year's question paper. Okay, am I audible?
Yes, ma'am.
Okay, fine. So once again, let us revise in short about SN1 and SN2 reaction. Okay, so one is SN1. One is, so let us first start with SN2 reaction. So SN2 basically it stands for nucleophilic substitution reaction. Nucleophilic substitution reaction. And here the 2 stands for, it is a bimolecular. It is bimolecular. For example, if I'm taking bromomethane and I'm reacting it with any aqueous base. So aqueous base, you can take KOH, NaOH or anything. So its counterpart is OH minus. Fine. So here nucleophilic substitution means we are going to attack the following compound with any nucleophile. And what do you mean by nucleophile? Nucleophiles are the species which are electron rich in nature. And what is the opposite for nucleophile? That is electrophile. So electrophiles are species which are electron deficient. So basically nucleophile, they have negative charge and electrophiles have positive charge. Okay. So, so here the nucleophile will attack on this carbon and Br is my living group. Okay. We'll see the mechanism, but now we are just writing the general reaction. So what will happen? This OH minus will substitute this bromine. So what will be my resultant product will be CH3OH plus Br minus. Okay. So OH minus substituted came in place of Br and Br is my living group. Now let us see the mechanism and let us try to understand why it is known as SN2 mechanism. Okay. Yes. Now, when you look into this carbon atom, what is the hybridization of this carbon? It is sp3. sp3, what is the geometry? Tetrahedral. Very good. So the hybridization of this carbon atom is sp3. So it is tetrahedral in nature. So let us write like this. So this is my tetrahedral structure. Okay. So in tetrahedral structure, this H and this Br is in same plane. This H, which is in solid bond, it is above the plane, and this H is below the plane. Okay. Now, in this respective reactant, we are going to add the reagent, that is a nucleophile. Now, from where the nucleophile will attach. So this is my front side, and this part is my back side. Now, this OH minus won't attack the this compound, this reactant from the front side. Why? Because bromine is also negatively charged species, and OH minus is also negatively charged species. And we know between two like charges there will be repulsion, right? So in order to minimize this repulsion, this OH minus will attack the carbon atom from the back. So we can write what with this OH minus will do, it will attack the carbon atom from the back side. And when it is attacking from the back, this bromine will leave the carbon atom. Okay. So what would be my transition state? It is somewhat like this. H. Now, in transition state, what we can see is that this Br is not completely removed on, and this OH is not completely bonded to this carbon atom. So there is partial bond breaking and bond formation. Okay, so this is my transition state. So basically, transition state is a kind of intermediate. It is the middle step where you can't isolate this transition state from the respective reaction. Okay, it only exists for few milliseconds. You can't even see, but you can predict it. Okay, this is the transition state where the bromine has not left the carbon atom, and the OH minus is not completely bonded with the carbon atom. Okay, and the final reaction and the final product will be what? This is C H, this is H. Okay, and here will be my OH, and my counter byproduct will be Br minus. Why Br minus? Because this Br has taken the bonding pair of electron. So as we know, carbon in the first reactant, we can see carbon and bromine. In between carbon and bromine, there is presence of a covalent bond. And what do you mean by?
They share ions.
Yes, one second. आ गया? आएगा भी. मैंने शर्वरी को कर दी, आप बस. Okay. Yeah. So there is covalent bond, and covalent bond means what? There is mutual sharing of electrons. Okay. So in carbon and bromine, there is presence of two electrons. Okay. Now this bromine, what this bromine did? It took the bonding pair of electron. Why? Why? Because bromine is highly electronegative as compared to carbon. And we know the elements, the atom, whoever they are, whichever atom are electronegative in nature, they'll attract the electron towards themselves. Okay. So bromine took the bonding pair of electron along with it. So that's why bromine is having a negative charge, and we are getting this respective product. Now, what we see is that in the first step, there is involvement of bromomethane as well as OH minus. And we also saw that this is a bimolecular reaction. So what do you mean by bimolecular reaction? In the slow step, when the rate of the reaction depends upon the two reactant. Okay, so there is presence of two reactant in the first step, that is bromomethane as well as OH minus. So we can say the rate of the reaction, rate equal to K molar concentration of CH3Br and molar concentration of OH minus. So the rate is depending upon molar concentration of two reactant. That's why it is bimolecular reaction, and this belongs to second order reaction. What do you mean by second order? When there is, when in rate determining step, or we can say in slow step, when there is presence of two reactant, or when two reactants are participating in this reaction, then that reaction is known as second order reaction. If one reactant is participating, then that would be my first order reaction. Fine. So SN2 is a nucleophilic substitution reaction where bond breaking as well as bond forming, they both are taking simultaneously. Like you can see, OH minus is attacking the carbon atom and Br minus is leaving the carbon atom. So this is taking place simultaneously. So this is SN2 mechanism. Fine. So when you look into the configuration, the conformation, so you can say in SN2 there is Walden inversion. So this is the question which they will ask in NEET exam. It is very important to keep this in mind. Walden inversion, which means in a living group, you can see this is present in this side, but in this the living group, the OH is present on this side. Other part has not yet been changed because the H is present in the plane. This H is present above the plane, and this H is present below the plane. So only the living group and the nucleophile position has been changed. Okay, so this is Walden inversion. Fine. Now let us talk about SN1 mechanism. SN1 reaction. Okay. SN1 is also quite simple. Okay. SN1 is nothing but it is nucleophilic. Again, same, it stands for nucleophilic substitution reaction. And this belongs to what one stands for? It stands for unimolecular reaction. So here there is involvement of one reactant at the rate determining step. Okay. Okay. So in this, let us see the general reaction. Again, the Br will get substituted by the respective nucleophile. So the nucleophile over here is OH minus. And our byproduct will be Br minus. Okay. Now let us see the mechanism. Okay. What is the nature of this carbon atom? ये बीच का carbon atom का? It is primary, secondary, or tertiary? It is tertiary. You just have to look to we are just talking about this carbon which is directly bonded to the halogen atom. So to this carbon, how many carbons are attached? Total 3 carbons are attached. So this belongs to tertiary carbon atom. Okay. Now let us see the mechanism. Then we'll try to understand more deeply. Okay. Now again, the hybridization of the central carbon is sp3, and sp3 means it is tetrahedral in nature. So two bond will be in the plane, one bond will be above the plane, and the other bond will be below the plane. That's it. We just have to keep this in mind. So here the CH3 and Br both are in the plane. One CH3 is above and the other CH3 is below the plane. Okay. Now we have the reactant. Now we are going to add the second reactant. In SN2, what we saw is that OH minus is it attacked the carbon atom from the back. Why? Because Br and OH both are negatively charged species, and to minimize that repulsion, so the OH minus attack the carbon from the back side. But in SN1 mechanism, the OH minus cannot attack the carbon from the back. Why? You do you know anything? What would be the reason for this?
Can you repeat the question again?
Okay. So in SN2 mechanism, we saw that the OH minus it attacked the carbon atom from the back side, not from the front side. And the reason for that was Br and OH, they both are negatively charged species. So in order to minimize that repulsion, the OH minus attacked the carbon atom from the back. But in SN1 mechanism, there is no any chance for the OH minus to attack the carbon from the back side. What would be the reason for this? You can try. If you're not getting, so we can solve it together.
In SN2, it is not getting any chance to attack from the back.
No,
SN1.
in SN1, yes. Okay, let us see. So why there is no any chance to attack the carbon from the back is that because of this bulky group which is present. This CH3, CH3 and CH3. They are the bulky groups which are present. So they are blocking the way for the OH minus to attack the carbon atom from the back side. And from the front side, there is no any chance. Why? Because both are negatively charged species, and between negative there would be there would be a repulsion. And when it comes to attack the carbon from the back, there is also no chance. Why? Because these all CH3 group, they are highly bulky in nature, so they are blocking the way for the OH minus to attack the carbon atom. So what is the only way is that first you have to remove this Br. And Br is a very good living group. You know why? Because they are negatively charged species, so they leave easily. So this Br will.
I mean, SN2, this thing are not present, like CH3, CH3, CH3. 3 CH3 is not present.
Could you repeat? I'm not able to hear you.
SN2 is in SN2. In SN1, it is not attacking from the back. You're saying this because it is because of the CH3. So I'm
Yeah.
asking in SN2, it is not present.
No, in SN2 there is no CH3. No, there is hydrogen atom. So this hydrogen atom size is not that much bigger than CH3. Hydrogen is a very small atom. So we can attack the OH minus from the back. We can so the OH minus can attack the carbon atom from the back side. Why? Because here the H atoms are very small. The atomic size is very small. So it is very easier. But when you look into methyl group, this three bulky methyl group, uh, they won't allow, they will block the passage, they will block the way for the OH minus to attack the carbon atom. You're getting it now?
Yes.
Okay. So the only possibility is that this Br minus has to leave this carbon atom. Then only we can attack. Okay. So this Br minus is a very good living group. We won't need any energy to remove this Br minus from the carbon atom. So this Br minus is leaving the carbon atom. So we'll get a transition state like this. Now this three methyl group will align themselves in such a way. So this is my transition state. Now Br minus has left the carbon atom with the bonding pair of electrons, so it is acquiring a negative charge. And the carbon, it has given its electron to Br, so it will acquire a positive charge. A carbon atom having a positive charge, we call it as carbocation. Any species having positive charge, they are known as cation. But in specific, if carbon is acquiring a positive charge, then that is known as carbocation. Done. Now this methyl group has aligned themselves in this manner. Now we can add OH minus. Okay, I'll just remove this bracket. Sorry. Now there is two chances. Okay, now there is no any blockage. Why? Because methyl groups have aligned themselves in a very good manner. So there will be no blockage for the OH minus to attack. Now
That is
OH
BR
minus. Huh.
in the case
Now
of BR.
yes. So the OH minus will have two possibility. One, it can attack the carbon atom from the front side. And what would be the product for that? It is somewhat like this: CH3, OH, CH3. So this is my first possibility. The next possibility is that OH minus will attack the carbon atom from the back side. Okay, why? Because there is in this transition state there is no any sort of blockage. Okay, because they have aligned themselves. So what would be my second possible product is that it would be somewhat like this: OH. These are the two possible product which we are getting. Okay, so this is getting in 50-50%. 50% this and 50% this. Now Br is in this side, right, in reactant, and in the same place OH minus is coming. So this configuration is known as retention. In reactant, Br minus is in this side, but in the product, in this part, OH minus is in this part. So in this opposite part. So this configuration is known as inversion. And when there is when there is 50-50% of inversion and retention, then that mixture is known as racemic mixture. This is also has been asked in Neet exam. What kind of configuration is seen in SN1? So there is racemic mixture. What do you mean by racemic mixture? It is a mixture in which there is 50% inversion and 50% retention. If in place of Br, in this Br is in my right side, and in this product OH is also present on the same side. So this is retention. This is the retained product of the respective reactant. In this part Br is in this right side, but in my product OH minus is in the opposite side. So what is this is inversion of the respective reactant. And if 50-50% of both has been formed, then that mixture is known as racemic mixture. You have any doubt now?
No, ma'am.
No. You're making notes, right?
Yes, ma'am.
Okay. Actually, sir is absent. That's why I'm taking the lecture. I'm just continuing the last week's topic which I've covered. Okay. I think you might have done this topic in your 12th class, right?
Yeah.
Yeah. Okay. Okay. Now let us continue with the chapter. Okay. Next part of this chapter is elimination reaction. Okay. The elimination reaction is like uh, when a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide. So there is elimination of hydrogen atom from beta carbon and halogen atom from the alpha carbon atom. So this particular reaction is known as beta elimination. So let us try to understand this part. So let us draw a general structure. Okay. So this is my X, this is my H. Okay. So your X, it denotes what? It denotes the halogen atom. So X is basically a living group, and living group in this part is a halogen atom. It can be fluorine, chlorine, bromine, or iodine. Okay. Now, the carbon which is directly bonded to the halogen atom is known as alpha carbon, and the carbon which is bonded to the alpha carbon will be my beta carbon, and to that beta carbon, the hydrogen which is attached is known as beta hydrogen. Okay. Now, in this part, we are going to add alcoholic base, alcoholic KOH. See, when we use aqueous, it would undergo nucleophilic reaction. In the above reaction, we saw Br is getting replaced by OH. But when we are using alcoholic, it would go under elimination reaction. Okay. So now we are adding any base. Consider any aqueous or alcoholic base. So what will base will do? It will abstract this beta hydrogen. So when you make one bond, you have to break one bond. So this beta, sorry, this sigma bond which is present between carbon and hydrogen, it is getting, it is breaking and it is coming in between alpha and beta. And this living group is leaving the carbon atom. See, whenever you are explaining any mechanism, one thing you have to keep in mind. You have to keep in mind that is the valency of carbon atom. The valency of carbon is 4, which means it is tetravalent in nature. You don't have to exceed its valency. Like you don't have to make its valency as 5 because that reaction is completely wrong. Okay. So you just have to keep this rule in mind, that is when you make one bond, you have to break one bond in order to maintain the stability. So the base is abstracting the beta hydrogen. This beta hydrogens, the bond is getting shifted between alpha and beta, and the living group is leaving the carbon atom. So what would be my respective product? C, single bond. This
It
hydrogen,
looks like it is Marconi rule.
uh, no, it is not Markovnikov rule.
In the Marconi rule, the thing will be the what halogen will be added. Here it is removing. That's
No,
only
it has
different.
been added. It has been added.
Then
In
it is the
Markovnikov,
Marconi rule, right? The Marconi rule also something is adding. But there will be a double bond. Here there is no double bond.
uh, yeah, there is a double bond, and we are not using base in Markovnikov rule. We are using HBr, we are using halogen acids like HBr, HI, like
Yes,
that. But here we
yes.
are using a base, we are using OH. So this is elimination reaction. Okay.
We are adding OH and what we are removing
We are removing in Markovnikov rule you're talking, or in this elimination?
in this elimination reaction.
In this elimination, we are removing this X atom, we are removing this halogen, we are removing this living group.
We are adding a base and we are
Huh.
removing the halogen.
In Markovnikov rule, there is like you are adding the negative part to the carbon-carbon double bond to the alkene system, but here it is an alkane system. Okay.
Yes,
Huh. Markovnikov rule is basically for unsaturated system, so you can't
yes,
go for saturated part. Okay, fine.
yes. Here it is saturated and it is single
In
bond.
Marconic, it is unsaturated.
Higher. Okay, clear.
Okay. Okay. ठीक है. Then this hydrogen bond is being shifted between alpha and beta. So here there will be presence of double bond. Then there is a carbon atom. To this carbon atom, there is two bonds. Okay. What is the byproduct? This base has been this abstracted this hydrogen atom, so we are getting BH, and this leaving group has left this carbon atom with the bonding pair, so it is having X minus. So this is my respective product. Okay. So this reaction is also known as beta elimination reaction. So we also call it as, okay. Now let us see one example. Even in elimination reaction, there is two type of elimination. बता सकते हो शर्वरी and gang? There is two type of elimination. नाम बताओ. One is, हाँ हाँ, नहीं नहीं. You remember any type of elimination in this? One is Sadzev and the other one is Hoffman. Hoffman तो नहीं पढ़े, but Sadzev is okay. So there are two type of elimination in beta elimination reaction. Sadzev and the other one is Hoffman. Hoffman is not included, but only for general knowledge. I'm just including this part also. Okay. Both are beta elimination, but the product which we are getting will be different. Both mechanism will be same, but the only difference is that the product will be different. Okay. So let us see one example. CH3, CH2, CH, Br, CH3. Okay. Now I'll just write one hydrogen like this and one hydrogen like this. Okay. Now I have added the base. Okay. The carbon which is directly bonded to the bromine will be my alpha carbon, and the carbon which is directly bonded to alpha carbon will be my beta carbon. So here you can see there is two beta carbon. One is this part and the other one is this part. So this is one beta, and let us name it this as beta prime. Okay. What the base will do? Base will abstract the beta hydrogen. Okay. So let us see first this possibility. What I'm doing, I'm just abstracting this beta hydrogen. This bond will get shifted towards alpha and beta, and this Br is been removed. So what would be my first product? First product is CH3, CH, double bond, CH, CH3. So this is my first product. What is the second possibility? The second possibility is that the OH minus will abstract this beta. This single bond is getting shifted between this alpha and beta, and this Br has been removed. So this is my second possibility. So this becomes CH3, CH2, CH, double bond, CH2. Now when you look into this two structures, you are seeing that the first structure, the position of the double bond is at the second position. So when you name this compound, this becomes 1, 2, 3, and 4. So this is becoming bute. So this becomes bute 2 ene. And when you're naming the second product, you're getting butene. Or we can say 1-butene. If the double bond is in the first carbon, so you need not to specify that carbon atom. It's of no need. Or you can even specify it if you're not getting it. Okay. Okay. Now, The first product is more substituted. So when you're looking, like if you're considering this carbon carbon double bond, and to that carbon 1 and 4 has been attached, that is, two methyl groups are directly bonded to this carbon carbon double bond, right? So this part will be my more substituted. And when you're looking into the second product, this carbon and this carbon is my double bond, but to this carbon only one carbon is directly bonded. This part is only directly bonded, but this is not. This is bonded to this carbon. So we won't consider this CH3. We are only considering the carbon which is directly bonded to the doubly bonded carbon atom. Okay. So here is only one CH2 been attached to the doubly bonded. So this is less substituted. So always remember, whenever we are getting more substituted alkene as a major product, then that reaction is known as Sadzev elimination. And if we are getting less substituted as a minor product, then that reaction is known as Hoffman elimination. In Sadzev, you are getting more substituted alkene, and in Hoffman, you are getting less substituted alkene. Both only it is possible when there is two beta hydrogen when it is present. Okay, if there is only one beta hydrogen in the above case, so it will only go for either of one reaction. Okay, so if there are two beta hydrogens, so there will be one major product and one will be minor product. The major will be more substituted and the minor will be less substituted. More substituted is following Sadzev rule and less substituted is following Hoffman rule. I hope you're understanding. You have any doubt now? So,
Ma'am, we are adding OH to remove this Br.
yes. OH won't remove Br. It is abstracting the beta hydrogen. You know, and when the bonding pair of this bond is been shifted between alpha and beta, na, so this Br is removed. It is been removed by the energy of this OH. Yeah. So in general, OH is actually helping the Br to get removed, but it is not actually removing the Br. Like it is directly not attacking like this. It is not attacking like this. Why? Because both are negatively charged species, and we concluded it that in SN2 mechanism only, it because of repulsion it won't attack the Br. So what is the next step? It would abstract the beta hydrogen and the bond will get shifted between alpha and beta and the Br will get removed because Br is a very good living group. So yeah,
Yes,
now you understood the difference between Marconic and elimination.
yes, ma'am.
Elimination, what are the main criteria? You need an halogen, you need a living group, and to that living group carbon should
Doesn't have double bond.
attach. Yes. And to that carbon, there should be a presence of beta carbon and beta hydrogen. So you need beta hydrogen and a living group. If it is present, and if you are using an alcoholic base, then that will definitely go under elimination reaction. If you have an alkyl halide and if you are using an aqueous base, then that time it would go under nucleophilic substitution reaction. And if you have a doubly bonded system and if you are using any HCl, HBr, then that would follow Markovnikov rule. And in that system only, if you are adding hydrogen peroxide, then that will go under anti-Markovnikov rule, or we can say peroxide effect. You got now? Actually, this chapter is very much easy. Like if you look into organic chemistry, now this is the easiest chapter of organic chemistry, where you can
Yes.
score very nicely. Because there is no any hard reactions to for you to keep in mind. You just have to make notes. You have to just make short notes, kind of reactant product. You can make like this. See, if you can make in this one page. You just have to make the partition. One is reactant. The second partition is for product. The third partition is for reagent. And the fourth partition is additional information. So for the first reaction, if the reactant is, for example, it's like this CCX, and here it is H. So this is alpha and beta. The product will be C double bond C. The reagent here is used as alcoholic KOH, and the additional information will be beta elimination reaction, or whatever you want to add keywords for you to keep this in mind, so you can write that. So this is how you actually revise the organic reaction, because for Neet you can't actually, like, if you have neat exam tomorrow and you are just revising the whole book, no, it's of no use. But if you're making like this kind of pages, or you're making like this kind of notes, so it is very easier for you to revise in 1 hour also. So this is how you actually revise organic chemistry, because in organic chemistry there are n number of reactant, there are n number of product, there are n number of reagents which you have to keep in mind. There are n number of name reaction as well. So you can't write each and everything, or you can't revise each and everything in one night. So you have to make notes like this, and you have to read every day. Okay, now let us move further. Just give me 2 minutes. Okay. Now let us move further. The next reaction which we are going to talk is about reaction with metals. So one reaction which is very much common, that is known as RMGX. RMGX is known as Grignard reagent. Very good. So RMGX. So we are just gonna look into that. Okay. So first reaction which we are gonna talk is about, that is Grignard reagent. In Grignard reagent, now what is the heading of this heading is that reaction with metals. So obviously we are gonna use metal, and the chapter name is haloalkane. So we are gonna use the metal. We are gonna react the metal with haloalkane or haloarenes or whatever. Okay. So we are taking CH3 Br. This is bromo methane, and we are using Mg, magnesium. Always remember, whenever you are using a metal, because metals are highly reactive. So even if metal comes in contact with water, it will definitely catch fire. So in order to ignore that kind of accident in lab, you have to use a system which should be completely dry. Dry means what? There should be 0% of moisture content in that. So that's why always remember, whenever you are using magnesium metal or sodium metal, the reagent is always it would be always dry ether. Dry ether means what? It has 0% of moisture content. Okay. Now, what will happen is that we are taking alkyl halide and we are taking magnesium. We are taking bromomethane and we are taking magnesium. And if we are treating it in the presence of dry ether, this magnesium will insert itself in between carbon and halogen. So what would be the product? CH3 MgBr. So this is my resultant product from the respective reactant. So what would be the name for this product is that this is methyl, this is magnesium, and this is bromide. So the product will be methyl magnesium bromide. And this reagent is known as Grignard reagent. And the general formula for the Grignard reagent is RMgX, where R is any alkyl or aryl group, magnesium, and X can be any halogen atom. Okay, fine. Now, if I'm treating this Grignard reagent, that is CH3 MgBr, with water, then what will happen? Let us see. CH3. Now I'll write this water as like this. HOH. This is also water, right? So in this, H is positively charged species, OH is negatively charged species. In CH3 and MgBr, MgBr will be positive and CH3 will be negative in nature. Why? Because when we look into carbon and magnesium, magnesium is more electropositive than carbon, so that's why it is having it is having positive charge. Now, you just have to rearrange this reactant. So what you will do? The positive part of this water will get attached to the negative part. Oppositely charged species, it will get attached. So what would be my resultant product? This positive will get attached to this CH3 part. So this will become CH3H plus. And this negative OH will get attached towards this MgBr, that is positive. So this will become MgOH X. So what is this? It is nothing but it is methane. So this is how you react. You solve this. Okay. Again, we'll take one more example. If I'm using, I'll give you one question. You just try it out. Okay. Will you able to solve this reaction? Hello, am I audible?
Yes, ma'am.
So I'll just okay. Just try this part and let me know what are you getting the product. So you can compare it with the following this reaction, this and this part. So you can solve this reaction. Just try it out.
Ethane. Answer is
Pardon?
ethane. CH3, CH3, CH. Yeah, ethane.
Final product you are getting what? B. You're talking about B, right?
Yes, final products is the ethane.
Ethane. So what would be the A product?
Is CH3, CH2, pH, MgBr.
Mg. Very
Yes.
good. Very good. You're right. So the A product will be CH3,
CH2, MgBr.
CH3, CH2, MgBr, and the B product will be ethane.
CH2, CH.
CH3, CH3, ethane. And the byproduct will be MgOHBr. So no need of byproduct, you just have to keep the main product in mind. So this is how the Grignard reagent works. Next reaction is very much simpler. It is also reaction with metals only, and that name reaction is Wood's reaction. The next name reaction is Wood's reaction. In Grignard reagent, we used magnesium metal, but in Wood's reaction, we are gonna use sodium metal. And everything you are gonna use in 2 moles. If you're using 2 moles of sodium, you have to use 2 moles of alkyl halide. Okay. So what will happen is that you're gonna use 2 moles of alkyl halide, and for this you're also using 2 moles of sodium. And again, I told you, if you are using sodium or magnesium, the reagent should always be dry ether. Okay. Now what will happen is that now let us write this 2 moles like this: CH3 Br, CH3 Br plus sodium and sodium. So this sodium, what it would be doing, this would take the Br along with it. So the resultant product which we are getting is 2 moles of NaBr. This CH3 and this Cl3 will bond together to form ethane. So if you are taking 2 moles of methane, you will get ethane. If you are taking 2 moles of ethane, then you will get butane. Okay, you just have to multiply it by 2. For example, if you are taking 2 moles of propane, CH3, propyl halide, CH2, CH2Br, and you're treating with 2 moles of sodium and dry ether. So if you're taking propane, propyl halide, so this is 3 carbons. So you have to multiply it by 2. So 3 twos are 6. So you will get 6 carbon atom ka hexane. CH3, CH2, CH2, CH5, and the last one is 6 plus 2 moles of NaBr. So basically, this is known as Wood's coupling reaction. So you are coupling two reactant together. Even if you are taking two different types of alkyl halide, then also it is known as Wood's coupling reaction. See, one more example. I'm giving you one example. Just try to solve it. Okay. Or you can tell the answer with the help of IUPAC name. Just try it out. I'm giving you 2 minutes, okay? ये लोग कहाँ गए? क्या नाम है? 11:30 को किसका लेक्चर है? Till 1:30. पल्लवी मैम भी यही आते हैं.
Adjurous butane.
Pardon?
Adjurous butane.
The product you're talking about, right?
Yes.
Okay. See, what you have to do is that you have to remove this 2Br with this 2Na. So you have to just bond this carbon with this carbon. So you have to draw this whole structure, and to this carbon just bond this carbon, and to this carbon this
Yeah,
whole
I
part
thought
of
it
the.
is just the left side of only one thing is a reactor. So I
Okay.
just said butane. I didn't
Okay.
see the symbol which is between plus.
Acha.
So there is totally 8 carbons.
Yes. 1, 2, 3, 4, 5, 6, 7. Yeah. Just I'll write the product.
Eight,
Can
nine
cross.
is there.
Yes, it is 9. 1, 2, 3, 4. And to this carbon, let us attach the CH2, C, CH3, CH3, CH3. Could you name this particular product?
7 means 15.
It is 1, 2, 3, 4, 5, 6, and 7. To the second carbon, there is presence of two methyl groups, right?
Yes.
So this becomes 2, 2
Dimethyl.
dimethyl, and the parent carbon is hept. And you can see that everything is single bond, so that becomes heptane. So this is 2, 2 dimethyl heptane. That's it.
Now, if it is 9 or 8, what will be the name?
Pardon?
If the carbon is 9 or 8, what will be the name? I forgot it.
8 is for octane and 9 is for nonane.
And 10?
Decane. Dec.
Okay, thank you.
Oh, welcome. Now, let us look into the next reaction. Reactions of haloarenes. So in that, the first reaction which we are going to study is nucleophilic substitution. The nucleophilic substitution which we studied further was for haloalkanes. Now we are going to start haloarenes. Haloarenes, which means when halogen is attached to a benzene ring, that is haloarene. Okay. Now let us see. Let us first see talk about resonance effect. To this, chlorine atom is attached. Now we know chlorine. The atomic number of chlorine is what? It is 17. Electronic configuration is 2, 8, 7. Right. So in the outermost shell there is presence of 7 electrons. Okay. And always remember the valence electron or the electron which is present in the outermost shell, they are only responsible in making the bond, in forming the bond. Okay. The electron which are present in inside the shells, inside the outer shell, they are helping towards shielding effect, so they are not that much important for making forming bonds. So the electrons which we need to form bond is the electron present in the outermost shell. Now chlorine has 7 electrons, so already it has contributed its 1 electron with making a covalent bond between carbon and chlorine. Now in 7 1 has gone, so total there are 6 electrons. So how we can write it? 1, 2, 3, 4, 5, and 6. Okay. Now, whenever chlorine actually it is showing a minus I effect, but now it is attached to a benzene ring, so it will be showing a positive resonance effect. So positive resonance means what? It is donating the electron to the benzene ring. So this lone pair of electron which is present over the chlorine, it will get contributed. It will get passed on towards the benzene ring. So again, when you make one bond, you have to break this pi bond, and this pi bond is getting shifted to the ortho position. So this is my first resonance structure, which would be somewhat like this. So this is chlorine. Now chlorine's bonding pair of electron, lone pair of electron has been contributed, so it has almost lost its two electrons, so it will acquire a positive charge. Now this bonding pair of electron has been this pi bond has been broken, and it got shifted to the ortho position, so this becomes minus, and this pi bond is as it is again. Now it would get stabilized. This negative charge will shift over here. This pi bond will come at the para position. So the next hybrid structure will be somewhat like this. This chlorine will be same. This negative charge has been shifted and will get a pi bond over here. This pi bond has shifted to the para position, so we'll get a negative charge over here. And here the pi bond is as it is. Again, the negative charge will shift at this position. This pi bond will shift over here at the ortho position. So we'll get a resonance structure which is somewhat like this. Sorry. So this pi bond is shifting over here. This negative charge is over here. We are getting chlorine and we are getting a positive charge. Now the negative charge will shift over here and chlorine ka positive charge will get stabilized. So we are getting the final hybrid structure is somewhat like this. Okay. So what is the need of this resonance structure? So when you are looking into this resonance structure, you observe that in A, B, C, okay, in this you can see the negative charge is present only in A, B, and C hybrid structure. So in A part, it is present at the ortho position. In B part, it is present at the para position. And in C part, it is again present in the ortho position. So the negative charge is present in A, B, C, that is ortho and para position only. So the substitution will also take place at ortho and para position only. In meta position, there would be no any sort of substitution, because to substitute uh, any atom or any molecule, we should have a specific charge on that particular compound in order to attract that compound towards itself. If it does not have any positive or any negative charge, so it won't be able to attract the particular compound. Okay. Let us understand this with one example. We are talking about nucleophile. Okay. In this, the first part is okay. I'm taking nitro is present at the para position. So this nitro, it is actually having a negative effect towards the benzene ring. So it is showing a minus I as well as minus R effect. So because of this effect, my this ring is highly reactive. It is highly unstable. So now I'm substituting. I'm the reaction is nucleophilic substitution. So the first reaction I'm using a reactant as NaOH base at 443 Kelvin, and in the second part I'm using acid. So what will happen now? We are just have to replace this chlorine with respective nucleophile. So in this nucleophile is OH minus. So we are just have to replace the chlorine with OH minus. So the following product will be somewhat like this: OH and NO2. Okay. So the reagent for this is, first we are using base and we are heating it at 443 Kelvin. And the second part we are going to add acid in it. Okay. What if what if I substitute nitro position at ortho position as well? So this would become like this somewhat. See, now nitro group is present in ortho as well as para position. So it is making the ring more reactive. So we are gonna use same reactant NaOH and second reactant as H plus, but we don't need that much energy to remove chlorine atom. So in this, the temperature which is used is 368 Kelvin. In the first part, we used 443 Kelvin, but in the second part, we are using 368. Why? Because there is two nitro group at ortho and para, so it is making the reactant more reactive. Okay. So the respective product which we are getting is, here we are getting OH, here there is NO2, and here there is NO2. Okay. What if I substitute nitro position at the second ortho position as well? So what will happen? The same thing will happen, but only the reagent is being changed. So here there is NO2. Sorry. So here are three nitro group which are present at ortho and para position. So it is making the benzene ring more reactive. So the reagent should be, very simple reagent. So we are just gonna warm the reaction. We're just gonna heat it, not heat it to like more than 100 degree. We're just gonna warm it till 30-40 degrees Celsius. And and in the second part, we are going to add H plus warm. Sorry, H plus. No, I'm extremely sorry. We are gonna warm it in the presence of water. The water will give its OH, and the chlorine will get replaced by OH. NO2, NO2, NO2. That's it. You just have to keep this reagent in mind. If there is one nitro, you have to add NaOH, H plus at the second as a second reagent. But in first reagent, you have to heat it at 443 Kelvin. In the second part, there are two nitro groups, so it is a bit more reactive than the first part. So you don't need much energy to remove that Cl. So you can just heat it at till 368 Kelvin, and the Cl will get replaced by OH. But in the third part, there are three nitro groups at ortho and para position, so it is highly reactive. So you just need to warm it in the presence of water, and the reaction will take place. That is, the Cl will get replaced by OH atom, OH molecule. Okay. One small part of this chapter is remaining, which we will continue in the next lecture, because I think at 11:30 you guys will be having physics lecture, right? So yeah, if we start this, so it won't end it in 5 minutes. So I hope every you understood today's topic. You getting it right?
Yes, ma'am.
Okay. If you have any doubt, you can ask me. Like if you are not understanding any specific point, you can stop me and you can ask me at that part only. Why? Because if you keep these doubts, if you say to yourself that I'll ask afterwards, but that afterward won't come won't come. So it's actually it's quite simple. If you get any doubt, you can stop me at any time, so I can clear your doubts as well. Okay, you just have to differentiate. You have to, if you're getting a reaction in your exam, first step is that you have to differentiate it, ki in which chapter this reaction is coming, or you can first you have to recall that in which chapter this particular compound is there. So if you are good in that and differentiating the reactions, so definitely your organic chemistry part will be damn easy in your NEET exam. Okay.
Okay, ma'am.
Okay, okay. One second. यही लिंक पे होगी या यही लिंक लीव करना पड़ता है? ओके। स्टॉप कर दूं? हो गया ना सर, मेरा गला बैठ गया सर। 3 मिनट कर दूं?